I'd like you to define for me the master law.
The master law is a central framework that describes the dynamics of stochastic physical systems by integrating concepts like conservative geometry, dissipation, interconnection ports, and stochastic forcing. It provides a unified way to model and analyze these systems using operators and geometric structures, making it easier to implement data-driven modeling, reduction, and control techniques. Does that give you a clear understanding?
Yeah, that's good. But I don't know what omega and lambda and psi and nu are in this system.
Great question. In the context of the master law, omega typically represents a generator or operator that describes the dynamics of the system. Tau lambda Tor refers to the operator associated with certain system properties, often related to energy or dissipation. Psa denotes the lifting function, transforming low-dimensional data into higher-dimensional features. Stats in nu are often associated with noise models, representing stochastic influences in the system. These components work together to create a comprehensive model of stochastic physical systems. Does this help clarify things?
Yeah, that helps. Now, I'm just interested right now in psi is equal to psi of x. What does that mean?
No need to apologize. In this context, sigma being equal to psi x means that sigma represents a noise model derived from the lifting function applied to the data x. This transformation helps to integrate the noise characteristics into the higher dimensional representation of the system. Does that make sense?
Yes, and when you're talking about lifted observables, are you talking about something like Koopman operators or DMD? What what other functions can use lifted observables?
Yes, lifted observables often relate to methods like Koopman operators and dynamic mode decomposition, DMD. They help analyze the dynamics of systems in higher dimensional spaces. Other functions that can use lifted observables include kernel methods for machine learning, nonlinear control techniques, reduced order modeling approaches. These techniques leverage the lifted structure to capture complex dynamics more effectively. Does that make sense?
Talk to me about Port Hamiltonian preserving projections together with Lipschitz or local Lipschitz drift.
Port Hamiltonian preserving projections are methods that ensure the structure of the system's dynamics is maintained when reducing the model. This is important for preserving energy and physical properties. The Lipschitz or local Lipschitz condition means that the system's dynamics do not change too rapidly with small changes in state. This stability is crucial for the effectiveness of the projections. Together, these concepts help ensure that when you reduce a complex system, it behaves smoothly and predictably, respecting its physical nature. Does this help clarify things?
Yeah, that helps. But I also want to know a little about skew as it relates to conservative dynamics and PSD as it relates to dissipative dynamics.
Sure, skew-symmetric operators relate to conservative dynamics because they preserve energy. They ensure that the total energy of the system remains constant over time, which is a core aspect of conservative systems. On the other hand, PSD, positive semi-definite, operators are associated with dissipative dynamics. They ensure that energy is dissipated or lost in the system, leading to stability over time. This captures the essence of dissipative behavior, such as friction or drag. Does that clarify how skew and PSD relate to conservative and dissipative dynamics?
Here's my final question about the master law. On a scale of 1 to 10, with 10 being the highest, how important is this master law relative to something like RSVD, plugging into a control system, plugging into a model selection, plugging into maybe a deep learning model?
The master law is quite important, likely around an 8 or 9 on that scale, because it provides a unified framework for modeling and controlling stochastic systems. While RSVD and deep learning techniques are valuable for specific tasks, the master law integrates various aspects like geometry, dissipation, and stochastic effects, making it a critical foundation for ensuring physical accuracy and robustness in control systems. Does that help clarify its importance?
Yes, but I'm also interested in how the master law would focus not just on, for example, the principal components, but on the principal components that are energy stable.
That's a great point. The master law emphasizes finding principal components that are not just mathematically significant, but also energy stable. This means the projections must maintain the physical properties of the system, ensuring stability during dynamics. This focus helps avoid unphysical results and ensures that any reduced order model respects the underlying energy structure of the system. Does that help clarify the distinction?
Yeah, but I have one more question about biological intelligence because what happened?
Of course, what's your question? I'm here to help.
I'm thinking about the energy parsimony of biological intelligence because a human brain, for example, only uses 20 watts in order to do massive intelligence. And so thermodynamics is critical here. And the master law, I think, is a step in the right direction.
That's an interesting perspective. The concept of energy parsimony in biological systems, like the human brain, ties in well with the master law because it emphasizes efficiency and stability in modeling. By integrating energy considerations, the master law can help create models that mimic efficient natural processes. Does this connection make sense to you?